Really?
All of that's custom.
That's cool. Yeah. I'm ready. Whenever you would like.
Hello, everyone. Thanks for coming by today. The Moravsky Lab has the very distinct pleasure of hosting Dr. Rob Ahrens. He comes so far away from Gainesville.
Yeah, right.
Just a quick ride. Rob Ahrens is a quantitative fisheries scientist and ecologist, and he did all of his training at the University of British Columbia. So he is in fact a Canadian, but he is here. I actually took a course this past semester with Rob, so I thought that he would be a great person to bring to the university. We can learn a little bit about fish and all of his experience he had with the Longline fishery. Let's see. So he has a lot of experience with assessment models. He's worked on single species models to more large-scale complex models. So if you have any questions about assessment models, he would be a great person to ask. Currently, he teaches 3 courses. This semester he's just teaching one. He told me, yeah. He teaches a quantitative stock assessment course, which I took, a natural resource class, this has a sampling class, and possibly applied ecology.
Field ecology.
Field ecology.
Running around looking at stuff.
Yeah, running around looking at stuff. So he's going to tell us why tuna is delicious, but we know that tuna is delicious, but other lessons learned from the Japanese longline fishery. So we're very excited to have you. We can't wait to hear.
Great. Thanks, Liz. And thanks to Steve's lab for bringing me down. Feel free to jump in at any time and ask questions if they come up. I'm quite happy to keep this pretty casual. I was told I've had 2 hours, was that it? Before everyone gets completely hammered and falls over. I was told I had half an hour about that, so this may be pretty quick. This is actually work I did for my thesis. I've kind of, after leaving it for a while, I'm kind of coming back to it and trying to look at where it fits into some of the fisheries in the Gulf and how some of the stuff we did there kind of works for some of the Gulf fisheries as we start to try and develop some new data sets. So I'll kind of end with where we'd like to take it for some of the Gulf fisheries. But really this is kind of an exploration of the history of the Japanese longline fishery, what spurred that analysis, and kind of where, kind of what I took away from it, and kind of, you can see some parallels in some of the stuff that is being put out in the literature now. So I like starting with this quote because I think it sums up fisheries assessment, if not fisheries science in general. So, how should scientists operate when we must try to explain the results of history? And in particular, those inordinately complex events that can occur but once in detailed glory. And I think that sums up what stock assessment scientists try to do. If we imagine almost any fishery out there and the incredible complexities, particularly the Japanese longline fishery, that really has been going since, I don't know, bluefin tuna Pacific was 1840, when really kind of the first commercial push in Japan started, and really things erupted after the Second World War. And if we think about the technological developments, the complex international relationships and fisheries that developed over that time, and the motivations behind them, as someone who is trying to use history to talk about productivity of stocks and what those stock potentials might be, if that's your chosen method for your assessment, then how do we go about it? What is that data telling us? And how can we use that data, or how does the data that we use influence the results that we get? And so I think it's a really nice place to start with. I don't know if anyone has seen this. This is kind of some Japanese protest art from when we were testing nuclear stuff in the Western Pacific in 1953. Don't know if I want to eat any of those ones. But so where did this come from? And really this is, what is that monkey doing, by the way? Also think about that. What's he doing? But the debate, and this really started in 2003 with the Myers and Worm paper that came out. I'm going to talk about lessons learned in terms of kind of the analysis part, but there were also a number of lessons learned about what can happen in peer-reviewed science and papers that get through, and checks and balances, and really the nature of scientific literature and the debate that occurs in it. But they came out with their article that said really rapidly after industrialization of fleets, there was a rapid decline in these large pelagics, not only just tunas and billfish, but also sharks. And roughly 15 years after the onset of industrialized fishing, they were depleted by 90%. And that came out, and that caused a debate in the literature, and people say, hang on, no, they didn't. How's that possible? We're still catching them now in more numbers than we caught way back then. How could they be down to 90? And then there were a whole bunch of discussions about, no, we haven't depleted them. They're still there, but we would expect them to deplete because we're fishing them, and they're at perfect levels. That's optimal. And then there were papers like the one that Carl came out that talked about complications in the way you use that data and you interpret that data. And there were questions about catchability, et cetera, et cetera. And so this is when I got into it. And I was fortunate enough to get hold of the Japanese longline data, which for the Pacific Ocean is not easy to get hold of anymore. And so I want to take you through kind of what I got from delving into this debate and where it went. But let's talk a little bit about the fishery before we go into it, because that's kind of a pretty cool story. So this is the catch of the Japanese longline fleet. The little orange dots here is catch that occurred during World War II. And so you notice there's a long history of this, and what's really interesting is the partnership also that was between the US and Japan and Cannery Row and all that kicked off in California prior to the war, and how that all kind of changed during World War II. But as we all know, when we had the war, fisheries reset globally, and they all rebounded back to pristine levels, and that is so. Okay? It is the truth. But then we have this massive eruption and catch from that Japanese fleet, and along with, because we're using long lines, these are pelagic long lines, so they're at the surface, hooks per basket, right, gangins coming off, various squid, but they catch marlins, and swordfish and spearfish and sharks and turtles and birds and all those things that go along with pelagic longlining. But Japan was really kind of the first fleet out of the gate in terms of that industrialization and expansion. And then if we look at kind of the global catch, it starts to take off and other nations come in. Korea comes in, the US is in there, Spain, France. No one knows what Russia did. I'm sure they have detailed records somewhere that none of us can get a hold of. But there's a couple things to note. Red here is skipjack, and that's really not a main longline species. It's really a bait boat or a purse seine species, and it is the dominant, the fleas of the pelagic ocean in terms of tuna fisheries, or the skipjack. The bulk of our biomass here is in the yellowfin tuna. It's really kind of the big biomass that they're pursuing. And then you have your higher value species, your albacore, your big eye, and then of course up into bluefin, and then the marlins and swordfish are this little bit right here in terms of the long line catch for the Japanese. The couple things to note that initially, early in this period, this was a canning fishery, and after the war it was as well. And so when you're putting things in cans, you're going for big biomasses, and then that fleet specialized, right? We had throwing out hemp-oiled lines with rope gangins and stuff like that on them. And then we had a development of monofilaments into that fishery, and then we had the big breakthrough in terms of Japanese, which was deep freezing technology. So the ability to, sub-zero your fish really quickly completely changed that market out there. And that fleet switched over from the less fatty yellowfin to the fattier big eye. The albacore fishery had been going on for a very long time, and the bluefin, so they completely changed the market out there. And so that fleet behavior changed. Also, gas started to get really expensive as you move through in the 70s, and you had some of the oil crises. And so a lot of the Longline fleet that, you see this tapering off, and this is because a lot of that switched over to purse seine. And so they moved, that fleet, really Japanese fleet, started to split off. Individuals who had long-lining ventures really shifted over into purse seine ventures. So a lot of dynamics going on there. Associated with those changing dynamics was this incredibly complex litany of rules for the Japanese in terms of who could fish where, given the corporation you were with and what you were fishing with. So this incredible complex mosaic of regulations about where and when you could fish. But the net effect of all of that was this. So we had, prior to the 1950s, just after World War II, we had the MacArthur Lines that were set up, and that really restricted the Japanese fishing fleet's activity in the western central Pacific. As that agreement aged, these lines, of course, were relaxed, and that fleet started to be able to expand, initially in the western. So this was the final MacArthur Line in 1950 that was eventually dropped, and then that fleet was allowed to expand across the world's oceans. So 1952, we're pretty focused in the western central Pacific. They start to expand eastward across there. They also pop into 1954, they're first right up in this area in the Indian Ocean, and they expand across that. 1956 really is the first appearance of that fleet over in the Atlantic, pursuing the yellowfin and bluefin complex that seemed to fall off the Amazon. And then, of course, they get this north and south expansion in the Atlantic Ocean. So a really kind of complex spatial dynamic and a complex diversity of that fleet. So the first thing we need to keep in mind then is, well, what was that fleet expanding over? What was going on? Before we get there, let's talk about this. There's also this complex spatial dynamic. So this bit of a fiddly graph. Indian Ocean, Pacific Ocean, Atlantic Ocean, various species, marlin, tunas, and swordfish. And then the black is high. The white is high, the black is low. And we're going seasonally here. And this represents effort targeted at those species. This is kind of this catch divided CPUE, this notion of relative fishing mortality rate. And what you should see is there's a pretty complex patterning going on seasonally in where that effort is being targeted given the spatial distribution of those organisms. In particular, you can see in the Pacific here that effect of the MacArthur Line kind of expansion in the first 2 years, and then kind of the expanse of that fleet. And so you get a spread not only spatially, but you get a spread of effort temporally in various locations. So some pretty complex space-time interactions happening. And of course, that's all occurring over this distribution. So this, I think, is the total, can't remember what I did for this one. It's the total catch by 5-degree cell of the major tuna and billfish species. So we have our skipjack, the yellowfin. Down here, we have the bluefin species that are all lumped into one. So there's your Atlantic, your southern, and your Pacific bluefin. Then big eye, albacore, and then we have, just for reference, these are the fisheries, regional fishery management organizations that set up the international agreements for tuna and billfish fisheries out there. So imagine this wave of fleets starting to move over this complex mosaic of species distribution and beginning to interact with them. And think about yourself as a scientist and how, if someone had asked you to go out and study the distribution and abundance, how you would go out and do it as a scientist in terms of designing your study, and then think about how the fishery went out and sampled that. And that is the problem that we have to deal with, right? That clearly the fishery is sampling it as an undergrad might sample it, where they start here and they're like, I guess I got to go out further and start collecting data out here, as opposed to someone who's like, wait, I actually have an entire sampling frame that is the world's oceans that I have to go out there and sample, right? So the Japanese fleet didn't do that. And so the big folly, if you would like, of the the Myers and Worm analysis was a failure to consider these time-area interactions that had gone on. And when we start to think a little more carefully about that, we start to get a very different picture of what went on in those fisheries. So this black line is nominal CPUE, and this is what Myers and Worm used, and that's total catch, right, divided by total effort. That's raw CPUE, nominal CPUE. The blue line is the average CPUE of those areas that were actually fished. So every area that had some fishing effort in it, right, we just average the CPUE from those areas, and we also get this pattern. This Poisson model down here is assuming basically a temporally stationary spatial distribution. And you're kind of doing this maximum likelihood estimation of the stationary distribution and then the abundance on top of that, and you're flipping back iteratively between those. And it's really akin, you can think of it something more that you would get if you would run a generalized linear model standardization on the data. It's kind of the pattern that you would get out of that. And the final line here is the kind of Carl's folly and fantasy fill. It's where you say, hang on a second, we can't, let's see if I can do this. We can't have a fishery that starts here and assume that the CPUE that they saw here for yellowfin tuna is the CPUE that they would see for yellowfin tuna over here. That just makes no sense. They didn't get here until, well, 1960. So what the heck went on over here before they got there? And what value do we put in this? So suddenly it's not what the fishery saw. It's like we have to go back to this picture and say, well, they started here. What value do I put in here? And how do I do that sort of data imputation? How do I fill in this entire grid of 5x5 cells in the world's oceans with values? And that's really the folly and fantasy argument says, figure out a way to do it. Because if you don't do it, right, you've made a very specific assumption. You're just probably not aware that you made that assumption. You've assumed that what's going on over here is exactly the average of what's going on in the areas that you observed. That's the only way, right? That's the hidden assumption that you've gone and made. So is there a better assumption to make out there? Is it 0? You know, so the basic folly and fantasy one that we used to fill here was said, well, let's just fill it with what we first saw and assume that hadn't changed, right, prior to when things got there. And then, of course, we were like, well, hang on a second. You can't do that. There's the environment, and tuna are big things, and they're zipping around the world's oceans. And that's true. But at least we've said something, and we've been really clear about it. And so our debate now is about how to fill this, right? And if you look at the latest paper that came out by Jim Thorson, he has this new Gaussian field method. That's kind of it's kind of a pseudo-Krieging way to do it. You could Krieg these fields, but you have to put something in there. Okay? And we'll talk about GLM standardization in a second. But the general pattern that you see is significantly different, particularly in things like yellowfin tuna that are the large biomass out there that drove the pattern in the Myers and Worm picture. Okay, so that relative big decline was driven by yellowfin. And what we see now when we put this line in is as global catches were increasing, yellowfin tuna were decreasing, as we would expect to see. Okay. These, I should also say, these were corrected for things like changes in gear configuration. We did that outside of this. But when you move into a GLM framework that tends to be a really critical step in stock assessment in terms of creating these relative abundance indices, and we come up with various linear models, right, if you're doing it in a GLM framework. What we found is there's two things going on. So if you read, Maunder and Punt have a really nice review. Rob Campbell has a really nice review, and it says you have to be incredibly careful about using GLMs for this. And traditionally what was done was you'd run a GLM, it would fit, and you would extract what's called the year effect. You'd say, well, that whatever coefficients go on the year, that's my relative abundance time series, right? So we just pull those out of the model, put whatever error I need to put on those on them, and there's my relative abundance time series. That turns out to be wrong, right? It turns out to be horribly wrong, in fact, in a number of cases. It also turns out that AIC, and I'll look at a table in a sec, turns out to be one of the worst metrics for determining what the best year effect is if you're going to extract it that way. Okay? And so if you do the year effect properly, so if you read Rob Campbell's, he says, no, you can't just pull that out. You have to predict CPUE across this entire grid of whatever you're fitting to the model, and then average across that. And that gives you a much better relative abundance trend out there. So that's the first thing. But he doesn't talk about data imputation. And so we're still missing, in this case, here's our nominal pattern. Here's our true pattern, which is the light gray. And the black is what we're getting by doing whatever method we're currently doing. And that's not working in some cases here. And in fact, you'll see as the model complexity increases, it gets worse and worse. And if we look at, of course, a metric of how well we're fitting to the true line in the simulation versus AIC out there, most complex model, AIC says go for it. It's your good one. And it's got one of the worst fits, right, to the actual pattern out there. So just, again, a warning that in terms of this sort of standardization, that you have to ask, what is the GLM trying to do? And the GLM is trying to predict the next CPUE point, right? This is, if I wanted to predict the next CPUE point, this is the best model to use. It is not the best model to extract the year effect from. Okay? So then we can move forward and we can move on to this spatial filling and say, well, let's just impute those missing values. We had these time area interactions. They were filled with nothing. Let's fill them with something. We can Krieg the surface. We fill them with what we first saw. And of course, once we actually do the data imputation, we're able to recover, regardless, of course, of the method that we're using, the relative abundance trends. Okay? So something that should be popping into your heads at this point is, well, hang on, you're making up data. And this is Bob sitting with stone crab claws making up data. Right? It's the same problem. But at least we're being transparent about it. And we can start to develop methods that hopefully work better. So there's the first thing that we learned. So once we had relative abundance time series, the next thing that we can do to them is kind of do